2212. To begin, what is our goal here? It is to float one positively charged tape with another below it, and then find the amount of charge Q on just one of the two tapes that are both identical in structure and length. As for models and physical principles, they include point particle model, Newton's gravitational law, electric force, and lines of charge. What will happen is basically the upper tape was in fact repelled by the lower tape and hence floated in the air sort of like this, letting us solve for Q by simply equating electric force with Fg. And now we go on to the actual equations. Newton's gravitational law can be stated as the following equation. F equals capital G m1 m2 over r squared, and this becomes a simple equation of just Fg equals mg for objects near the Earth's surface, where g equals 9.8. The electric force, where k is Coulomb's constant, or 1 divided by 4 pi epsilon naught, is similar. It's Fe equals kq1 q2 over d squared. Point charges each have an electric field, but complex shapes are composed of many point charges, like this rod, for example, that sum to an electric field, a superposition, as shown in the diagram below, of this positively charged, radially outward pointing charged rod. As for my experiment, the system is just the upper tape by itself that was floated in the air, and everything else is surroundings. For example, the other tape or the wall or the air are all surroundings in the system here. I gathered the following measurements for my physical experiment. The tapes were all 0.2 meters long and 0.002 kilograms in weight. And they also had a separation distance of 0.025 meters when they were separated apart in their floating motion, I guess. And with the equation F equals mg, the gravitational force in this equation is equal to 1.962 e negative 3 for just one piece of tape. And because the system is in equilibrium and the only other force is Fe, we know that the magnitude of Fe is equal to the exact Fg. So it's 1.962 e negative 3 as well. As for more details, the equation for the electric force given the electric field is equal to F equals QE, where E is the electric field and Q is the object's charge. Both tapes had the same charge, so we simplified the equation to get electric force equals kq squared over r squared, and plug in the separation distance for r in this instance. Setting the formula equal to the known values of 1.962 e negative 3 and solving for Q, we get Q equals the following value of 1.17 e negative 8 coulombs for one individual particle in this model. Here's my image as well as my video from my experiment and how I set it up. It's pretty simple, just tape that's charged and it tracks your finger, as well as tape that's hanging up in this sort of horizontal position, I guess. I'm not sure how to describe it, but yeah. As for the actual coding, here's my code for the point charge system. As you can see below, Q equals 1.170 negative 8 coulombs for this instance of one piece of tape as one particle for each piece of tape in this case. So here's the model as well as the code. Here it is for the line charge 2, which shows the 50 plus particles within the longer rod as a more accurate model. And the Q in this case is 2.51 e negative 8 coulombs, so it's more accurate, and also it's bigger in this case with more electric field for, a larger representative model. So here it is. As for my assumptions and errors, this is assuming that both tapes are point charges, which is definitely an exaggeration and abstraction from reality to make calculations easier for us. And even the line charge isn't fully accurate because there are way more charged particles than just the 50 we show in this model. And we also assumed that the pieces of tape had equal charge, even though variations in length, malformations, and time elapsed would affect that a lot. We simplified the system to only have two forces acting on it, although there were many more than that, including air resistance, tension, and contact forces as a small list of examples. And here are some questions. What if protons and electrons switch their charges? In this case, the tape pieces would still repel each other, but they would also repel negatively or neutrally charged objects, like, for example, the pen or even my finger, instead of attracting them like they did previously. And also, how are the two models' results for charge different? The line charge model's estimate is roughly 2 times the amount that of the point charge because it takes in more particles into account and calculates the stronger electric field. The line charge model is also more accurate than the point charge because it more closely resembles an actual piece of tape, which probably has a gazillion or more particles in it compared to the just one particle in the original Model 1. And that's about it from my video. It's possible to model charged objects with 1, 2, or even 100 points or particles in this case, but their nuanced interactions should be properly represented using integrals in order to account for that many charged particles in this case. You can show that these cool magic tricks with floating tape and attracted objects to kids if you want for a cool magic trick demonstration. And that's about it for my video. Thank you for watching, and goodbye.